So welcome to the sixth lecture of Mathematics for Minor Finance. So today we're actually going to talk about integration, and as we'll see, integration, that's basically the opposite of differentiation, so of taking derivatives, which we have done so far quite a bit. So we're going to look at, well, first of all, at the indefinite integral, which basically explains how to do the inverse of taking a derivative. Then we're going to look at the applications, which are basically definite integrals. So definite integrals will be seen to be related to areas under graphs, so areas under functions, graphs of functions. It will use those to look at a finance application, also a probability application, and to also look at a microeconomics application in the computation of consumer surplus and producer surplus. So that will be the very end of this lecture. So all those things will be applications of integration. So let's have a look at what that means. So what's integration? So let's look at again some function. Let's call it little f. And we know that if you have some function little f of x, then we can of course take the derivative. So if I look at all these rules for taking the derivative, the product rule and the quotient rule and the chain rule and what have you. So we know how to take derivatives. Now the opposite question would be, well, can we actually find a function, let's call it capital F, which if we take the derivative of that capital F, then we get our original function little f back. So what would that mean? Well, suppose our original function would be 2x. The question would be, can we find some function which, if we take the derivative of that function, it would give us 2x? Well, if you think a bit about this, perhaps you already have recognized, well, of course, this function x squared actually does the job perfectly. Because if I take the derivative of x squared, well, the 2 goes down, so it comes in front. The power goes down by 1, so it becomes x instead of x squared. So indeed, we have 2x. So what's this c doing here? So actually, if we look at x squared, of course, the derivative is going to be 2x. But if you look at the function x squared plus 1, say, we would also get 2x because this 1, a constant. If you take the derivative, this constant vanishes, right? The derivative of a constant is 0. So x squared plus 10, again, the derivative would be also 2x. So any constant that you add to this x squared here, let's call this any constant c, just a constant number, that will do as well. So we can add any constant to this function x squared and still have a function which, if we take the derivative, gives us back 2x. So basically this is what integration means. Find, given a function little f, which here's 2x, find some function, or actually a whole family here of functions, which if you take the derivative gives this 2x. So any x squared plus some constant, whatever this constant is, will do that job. And as I just mentioned, actually, so we are going to use this, it's sometimes called the antiderivative. So the integral is sometimes a different name for the integral is the antiderivative. You sometimes see that name. So applications of this integral or of this antiderivative are that they compute areas on the graphs. And these areas on the graphs often have meaning. So in statistics, perhaps you know that areas on the graph, say an area under the bell curve, for instance, under the standard normal distribution, has the meaning of a probability. And in finance, we'll see that if you have two valuable streams of cash flows, so many different cash flows together, often this is most easily done by computing an integral rather than just adding up different cash flows, lots of different cash flows. And the microeconomics, as I just mentioned, if you want to have a look at surplus, particularly at consumer and producer surplus, and perhaps you recognize this picture as doing that, you also are again involved with computing areas. So again, areas are computed. You're using derivatives, using integrals. So for computing surplus, consumer surplus, producer surplus, we are again going to use integrals, integration. So let's have a look. So again, the definition is, suppose we have to find the integral of some function little f. So how do we write this? For a bit of notation, we write this funny looking S symbol in front. Actually, it comes from an original S for summation. So we'll see what it has to do with summation a bit later on. But this symbol is an integration symbol, and you write a dx after this, where this x is the variable that you're integrating over. So it's the variable that sits in this function x that you're sort of computing the integral of, that appears here as d that x. So this question asks, so this notation means what is the indefinite integral of this function little f? And the answer will be, well, some function capital F of x plus any constant, where this capital F is chosen in such a way that the derivative of that capital F is the little f that you're after. Just like before, the little f was 2x and the capital F was the x squared. So x squared plus any constant in this case were an indefinite integral of the function little f equals 2x. So we're going to have a look at how to determine these indefinite integrals. So first we'll have a look at some basic functions, particular power functions and exponents, exponential functions. Then we look at some rules, constant rule, sum rule, multiplication by a constant, so adding up different functions, so what happens then. We'll have a little bit of a look at rewriting functions in order to be able to compute the integral, the indefinite integral. Sometimes actually it just helps to have a good sudden flash of insight and then use trial and error to check whether that flash of insight indeed gives us the desired function. And sometimes it turns out that there is actually no function that we know that has been predefined that gives, if you take the derivative of any function f that you want, like e to the power x squared, it doesn't have an explicit integral in terms of function that we know of, so you have to define it separately as the integral, basically. So if we look at that too. So first look at some basic integrals, in particular look at power functions. So if you have some power x to the a, so the function is x to some power a, and let's take a not equal to -1 because that's a special case. So can we find the indefinite integral of x to the power a? That's what this first line says. And the answer is yes, we can. What does it look like? Well, again, like a power function, x to the a plus 1. That almost does it. The question we should ask is, does this function, if we take the derivative, indeed gives us x to the a? Well, if we take the derivative of x to the a plus 1, the a plus 1 goes in front, and the a plus 1 is reduced by 1 to get a, so that gives us the x to the power a. A plus 1 goes in front, so somehow we have to get rid of that, and that's why we have this prefactor here. We divide also by a plus 1, so this a plus 1 which goes down to the front here will cancel against the a plus 1 in the denominator here. And you can see indeed a is not supposed to be -1 because then this trick doesn't work. So this function indeed will be the capital F associated to the little f x to the a. And of course we have to include this plus c, so adding any constant, adding +1, adding +0, adding +100, all those will do as well. So we denote this by adding any constant c. So what's this exception? A equals -1, then this rule does not work. So in that case, what we get is the logarithm. The logarithm of what? Well, of x, we would like to say, because we know that the logarithm of x is 1 divided by, the derivative of that is 1 divided by x, but of course that only works if x is positive. So we somehow have to make this x positive. So let me do that actually on paper so that we can see what this means and why this works. So now let's go to paper then. So first of all, let's write what we had. So we had this rule. So in general, x to the a dx. This asks what's the indefinite integral of x to the power a. Let's assume a is not equal to 1. So the claim is it's almost x to the power a plus 1, because if we take the derivative of x to the a plus 1, the ddx of x to the power a plus 1 is a plus 1 times x to the a, we know that. So a plus 1 goes down by 1, but we get the a plus 1 up front. So well, the x to the power a is what we need. What we ordered. We wanted this to be x to the power a, but we have this annoying a plus 1, which you have to get rid of. So just divide by a plus 1. So that gets rid of the a plus 1. So this is it almost, except that we should not forget that we can add any constant to this. So this was this first rule. So now this second rule, the exception. So the question was, do we know a function which gives x to the power minus 1 as its derivative? And of course, x to the power minus 1, we recognize that as 1 over x, right? That's the same thing. So which function does that job? Well, we know that the x of the log of x equals 1 over x. So this does the job, we would say. So this is just it, and add a constant to that, except this only works if x is bigger than 0, because a log of x only defined for x is bigger than 0. So that for that reason, we are actually going to add these two lines, which mean the absolute value of x. So what does that mean? Well, given some numbers, say number 5, the absolute value of 5 is just 5. So it's just that same number. But for a negative number, minus 5, the absolute value is also plus 5. So what these two vertical lines, or the absolute value, do, they tell us what's the value, well, except that we want to get rid of any minus signs that are in there. So that's what the absolute value means. And so what's the absolute value of x? Well, if x is positive, then of course the absolute value, well, it's already positive, just like the absolute value of 5 is just 5. The absolute value of x is going to be x. But if x is negative, then the absolute value of that negative x is going to be the positive one. Well, that's minus the negative one, right? So if x is negative, then minus x is again positive. So the absolute value of that negative number is actually minus x if x is a negative number. So that's why we have this log of x. Let's check whether that works. So if x is bigger than 0, again, the dx of log x is well defined, because log of a positive number, we can deal with that. That indeed equals 1 over x, and that in turn is x to the power minus 1, which we wanted. So that works. If on the other hand x is smaller than 0, you would like to take the ddx of the log of minus x. So x is smaller than 0, so minus x bigger than 0, so the log of minus x works in this case if x is smaller than 0. What's a ddx? Well, we have to use the chain rule, right? So there's a minus in here, so let's use the minus. If you use the interior function, it's just minus x, so it gives us a minus 1. And the exterior function is a logarithm. Well, what's the derivative of that? Well, 1 divided whatever is in there, so 1 divided by minus x. And indeed, these minuses are cancelling out. So again, this gives 1 divided by x. So in general, the dx of log of the absolute value of x indeed is 1 divided by x. So this works. So that's some preliminaries. So let's see how this works for some examples. First, no, let's look at the original regular powers that we have here. So let's ask, what's the first example, what's the indefinite integral of function x? So again, this integral symbol, this s, means what's the integral. Dx is the integration variable, so what is this function a function of? Well, of x. See, a simple function fx is x itself. Can we find a function which, if we take the derivative, gives us back x? And the answer is yes, we can. Is it x squared? Well, almost, because if we take the derivative of x squared, we get 2x. So we have to divide by 2 and multiply by half. To indeed, if we take the derivative of this object, we indeed get 2 divided by 2 is 1 times x, what we need, x. And remember, we have to add any constant to this. So any function of the form half x squared plus some constant will do as the indefinite integral of x itself. And if you compare this with the a equals 1 case in this general rule, you'll see that that's precisely what's happening. So with a equals 1, we have power 2 here, and we have 1 divided by 2 in front, which we have here. That was the first example. So second example is 1 divided by x to the power 3, x cubed. Is this power? Yeah, it's a power in the sense that we can rewrite this as x to the power minus 3. So remember, that's the same thing. X to the power minus 3, that's 1 divided by x over 3, x to the power 3 dx. So this again is of this form, x to the power a dx, where the a is now minus 3. So can we integrate this? Well, we have to raise this power minus 3 by 1. So minus 3 plus 1 is going to be minus 2, right? So if I take the derivative of x to the minus 2, this minus 2 would drop to minus 3. So that's nice, but the minus 2 gets up here in front, so I have to cancel that. We cancel that by adding this minus a half in front. And again, we have to add a c here. So that's the second example. The third example, so all these examples are on the slides as well, is this one. X times square root of x. What's the indefinite integral of x times the square root of x? Well, you remember that the square root of x is x to the power a half, right? So this is a function, if you wish. X to the power x to the power a half. So x times x to the power a half, that's x times square root of x. What's the indefinite integral of that? Well, if I multiply x to the power 1, which is basically x to the power 1 times x to the power a half. If I multiply two powers, I have to add up the exponent. So this is actually the integral of x to the power 3 halves, right? 1 and a half dx. So now we're in business again, because this is exactly of that form. So what do we have to do? We have to add 1 to the power here. So it's x to the indefinite integral will be something like x to the power 5 halves. So 3 halves plus 1 is 5 halves. 1 and a half plus 1 is 2 and a half. But if we take the derivative of this, we get 5 halves in front. We want to get rid of that. We do that by multiplying by b inverse 2/5. And of course, we have to add c. And if you again plug in a equals 3 halves in our general formula, this is actually what's going to work. Okay, so let's get back to the slide then. So here are those examples again. So x to the power 1, the integral of that is just x squared a half times x squared plus a constant. 1 over x cubed, that's x to the power minus 3, again over this general form, turns out to be minus a half times x to the power minus 2. X to the power minus 2 is this 1 over x squared, right? Plus a constant. And the final one, x times square root of x is x to the power 3 halves, so we can use the general rule to get this 2/5 times x to the power 5 halves plus a constant. So the next natural function that we would like to be able to take the derivative of is the exponential function. So the general rule here is e, if we have some e to the power ax plus some b, what we need as well, what's the function that we need, which if we take the derivative gives e to the power ax plus b. Well, if you look at this a bit, you see this thing actually does that job, because if we take the derivative, the a is coming down by the chain rule. So think about that, check that. By the chain rule, the a is coming down, so I'm going to cancel this 1 over a. And the derivative of the exterior function, the e to some power, is just e itself, right? So e remains as e to the power ax plus b. So if we take the derivative and do that, just check that you see that that works. Of this object here, you'll see that produces the function that we have here under the integral sign. And of course, again, we can add any constant c to that. So it's not going to work for a equals 0, because then it's just a constant, of course. In general, actually, we can learn by heart this particular rule. So I never do this. I just convert this into a natural exponent. So let me show what that is on paper again. So I'm sure you, if you think about this and might want to do this yourself, and pause this video, be my guest. So write a to the x as some power of e rather than some power of a, and see whether you understand why this solution comes out. And let me then, after you have come back to this, after you have paused the video, let me do this on paper. So there we go. So we have the indefinite integral of a to the x, and now we note that a is of course e to the power the log of a, right? So a to the power x is actually e to the power the log of a to the power x. But we can rewrite this, of course, a power to a power. What do? You multiply the powers. So e to the power x log a. So can we now use that? Yeah, of course. Well, what we're going to do is going to make that substitution, if you wish. We write this as e to the power x times log a. We're integrating over the x. So question, can we find a function which, if you take the derivative, it gives us e to the power x log a? And my claim now is, yeah, we can, because it will be almost e to the power x log a itself. Because if we take the derivative of that, it's going to be e to the power x log a, because the derivative of the exponential is itself, except that we have, by the chain rule, there will be a log a in front. So we have to cancel that log a, which will come down by dividing by log a. So 1 divided by log a times e to the x log a plus a constant is here the indefinite integral. And of course we can now write this back as what we had, e to the x log a. And so this one is of course again a to the x. So this just says a to the x divided by log a plus constant. So if you make it a habit of rewriting any a to the x into e to the power the log a times x, then you don't have to learn this rule by heart. But if you prefer to learn a rule by heart, be my guest. That's also fine. So let's use our knowledge about the integration of e to the x by doing an example. So the example here is, which will also be on the slide again, e to the power 1/4 x plus 2. This function we want to integrate. So the question again is, can we find some function which, if we take the derivative, gives us back this e to the power 1/4 x plus 2? Answer is, yeah, we can. It's almost e to the 1/4 x plus 2 itself, except that if you take the derivative of that by the chain rule, this 1/4 will drop down in front of it. So you have to multiply this by 4 to cancel that 1/4, which will come down. So this is the answer, except that again, we have to add c to this. So this was the exponential function and its indefinite interval. Go back. And here you see that example on the slide as well. So let me then see how we can combine various functions. So we now know some basic functions. Well, the simple rule here is if you multiply some of these basic functions by any constant, let's call it a again, that just means multiplying the integral by the same factor a. You can verify that by using the constant multiplication rule for derivatives. And same ways, if we have a sum of two functions, then its integral will just be the sum of those two indefinite integrals. So that's pretty easy. So what we don't have, at least we are not going to cover that, and there's some similar extension here as well, which exists, I can say, but which we are not going to do, is an equivalent of the product rule. So we know the product rule for differentiation and the quotient rule, which is related to that. We're actually not going to look at that in this course. So there is something which is called partial integration, and of course, if you're curious, do have a look because it will be in your book, but we're not going to use it in this course. So in this course, we'll just have to work around products. So how do we work around products? Well, here there is a product. So can we do anything with this particular function? So it's a function we want to take the integral of x squared plus 1 times x plus 3. Well, so problem, we have a product. I didn't tell you what the product rule is, so can we get around this? Yeah, we can by rewriting this product actually as a sum. So it's here, but let me do it for you on paper. So this example was x squared plus 1 times x plus 3 dx. So what's the indefinite integral of the function x squared plus 1 times x plus 3? So this is a product. Problem, how do we deal with the product? Well, let's just expand this product. It becomes a sum of powers. Why is that? So if I expand this, so get rid of the brackets, in other words, what do we get? Well, the first term will be x squared times x. That's x to the power 3. Then we have an x squared times 3, so it gives me 3x squared. Then we have the 1 times x, so it gives me plus x. And finally we have a 1 times 3, so it gives me plus 3 dx. Now all is again well, because here we have just a sum of powers. Can we deal with the sum of powers? Yeah, the indefinite integral of a sum of powers is just the sum of the indefinite integrals. So we'll do that. Well, the indefinite integral of x to the power 3 is going to be x to the power 4, except that I have to divide by 4 to get rid of that 4. The indefinite integral of 3x squared is, of course, x cubed. And now actually this 3 is precisely what we need. So we don't have to do anything else, because the 3 will be coming down to provide exactly the 3 that we have here. Indefinite integral of x is a half times x squared. The indefinite integral of the constant 3 is 3x, because if I take the derivative of 3x, I get 3. And the only thing that's lacking here is that we have to add a constant. So this is the answer. So what we have to do if we see a product, usually it's a good thing to expand the product into a sum of terms, and then we can do the integration on each of these terms themselves. And so let's look at one more example now involving a quotient. So the quotient here is x to the power 3 minus 3x plus 4 divided by x, and that I want to compute the indefinite integral. So again, I didn't tell you any quotient rule, so we cannot use any quotient rule here. But again, we can expand, right? So let's do that. Let's expand this fraction here in different terms. So what are those terms? Well, the first term here is going to be x cubed divided by x. That's going to be x squared. The second term is minus 3x divided by x. That's going to be minus 3. And the final term is going to be 4 divided by x. So this is the same thing. So note that I used here, I sort of carelessly crossed out these x's over here. That only works if x is not equal to 0. So this integral is actually only defined for x not equal to 0. Right? So now we have a nice sum of terms. Can we integrate each of these separate terms in the sum? Well, yeah, of course. We have learned how to do that. So how do you do that? The first x squared here gives us x to the power 3. I'm going to do the integration, of course. I'll get rid of this integral symbol. So the first term is x cubed divided by 3. So that is, if I take the derivative of that, I get the x squared, which we need. The second one, what we need is minus 3x, because if I take the derivative of minus 3x, it will be minus 3. This minus 3. Finally, 4 divided by x, and here we encounter our logarithm, right? So this was this example that we had above here. D dx of the log of x is 1 divided by x. We're going to use that. So do not forget here that we need to include these absolute value lines, right? 4 times the log of the absolute value of x. And you have to add any constant c to this. So this bit here is the integral of what we started out with. So again, we've rewritten this quotient a bit into a sum of different terms, and each of these different terms you can indeed integrate to get this particular outcome. So here we had this example product that we reworked into a sum, and here we have this quotient that we reworked as a sum. So the same thing that I just did. Final way in which you can sometimes do an integral is just by guessing. Well, we have an educated guess, because otherwise you will be probably wrong, but sometimes you just have this flash of insight, or somebody provides you with a flash of insight. It might be something like this or that. Can we check this? And now the question is, well, if we can check it and it's true, well, then it's okay, right? So let's try to do that. Suppose I tell you, can we check, might it be the case that the integral of the log of x, which remember we have not yet covered, what's the integral of the log of x? Well, it's a bit more complicated. Telling you it's x log x minus x, plus of course any constant c. So can we check whether that's actually true? Well, what does it mean? Is it indeed true that if you have the function x log x minus x, and we take its derivative, that we get back the log of x? So let's see whether that works. So let me remain on the slide here. So let's look at the first term, the derivative of x log x, the derivative of a product, right? So I have to use the product rule for taking this derivative. So the first part is operating the derivative on the first function x times the second function log of x. The derivative of the first function is 1, right? The derivative of the function x is 1 times log x. Then we have to take the first function, the x, times the derivative of the second function. It's going to be 1 divided by x, or x to the power minus 1. So that gives us x times x to the power minus 1. And the derivative of this final minus x here just gives us minus 1. So does that bring us further? Yeah, so this first part gives us log of x. The second part, x times x to the power minus 1, x times 1 over x, is going to give just 1, minus 1. Well, these ones are cancelling, so we get exactly log of x. So what we just did was, well, we were given this guess, and we checked that that guess actually works, in the sense that if we take this guess and take its derivative, it does provide the log of x, the function that we were after. So indeed, x log x minus x plus any constant is the indefinite integral of the log of x. So that's what we learned here. So that's indefinite integrals, and next bit will be about the definite integral, which we're going to use for doing actual computations.